It's a great honor to introduce my friend and colleague, Amie Wilkinson. And I have known Amie for, I guess, more than 20 years since she was a postdoc at Harvard and I was a grad student. Amie is a professor of mathematics at the University of Chicago, where, as it says on the slide, where she specializes in smooth dynamical systems. She is a fellow of the American Mathematical Society, our favorite professional organization, and also a foreign member of the Academia Europa. She was the winner of the 2011 Satter Prize for a body of work which is centered on her 2010 paper with Burns on partially hyperbolic dynamical systems. And she won the 2020 Levi Conant Prize for her article on the Lyapunov exponents, which is great, by the way, which is published in the notices. She's also the chair of the IPAM Science Board, on which I serve. And it's really through that service, serving on that board together with her, that I've just come to see what a universal mathematician Amie is. I mean, we talk about dynamics, we talk about number theory, we even talk about particle accelerators. Actually, really, Amie talks about that and I listen. Anyway, today she's going to talk about dynamics at the very heart of her interest. And I just want to thank her for accepting the Society's invitation to give this lecture. And now let's all enjoy.
Thank you so much, Jordan, and thank you to the AMS and MAA for this invitation. It's a real pleasure to give this talk. When I was initially giving this talk, I kind of forgot what talk I was giving, and my husband looked over my shoulder at the talk I was writing. He was like, "What the hell are you doing? This is like a public, I had to go back and look at the instructions, and I saw, yes, this is a expository / historical, a historical and expository kind of flavor this talk should have. And fortunately, the subject lends itself incredibly well to expository and historical discussion. So let's start with symmetry. What is symmetry? So I think most of us have a good idea of what is a symmetry of an object. So a symmetry of an object, thinking of an object in space, is a motion of the space that leaves the object unchanged. So given the time of year that we're, at least in the Northern Hemisphere, enjoying, my favorite object to examine is the snowflake. And this object has several symmetries. For example, I could rotate it by 60 degrees and I get the same snowflake, more or less, ideally. Or I could do 120 degrees, same thing. Or if you flip it over, and now this has been flipped twice, again, that's a symmetry. So in general, symmetries of objects, I think are the most natural way to introduce the concept of a group, because the inverse of a symmetry is a symmetry, composition of symmetries is a symmetry, and it satisfies all the group laws. So symmetries of an object form a group, and in this case, the symmetry group is the dihedral group, which is also the symmetries of the hexagon, and this is sometimes called the snowflake group. The subject of this talk is not symmetries of objects, but symmetries of dynamical systems. Now, what is a dynamical symmetry? Well, we'd like a dynamical symmetry to be such that if the dynamical system produces some canonical object, that the symmetries of a dynamical system produce symmetries of that object. And here's the natural way to define a dynamical system. So for the purposes of this talk, a dynamical system is a smooth map from a manifold to itself. Smooth meaning at least C1. And I'm going to keep track of the degree of regularity. So some number R could also be like complex analytic, but I'm going to impose usually some differentiable structure here. So if you want, M is just Rn, and at least for most of the talk, that's fine. For later on, maybe M is the sphere or the torus, something compact. And this is what I call a dynamical system. So why dynamical system? Well, when you have a map whose domain and codomain are the same, you can apply that map repeatedly. And you can think of the repeated application of that map as the evolution of some system over time. So you start with a point X in M, and if you apply F to that, you get F of X. And if you apply F again, we call that F squared of X, and so on, cubed of X, And this is called the orbit of the point X, and it represents kind of a trajectory over time, if you want to think of it that way. And so this superscript here denotes a unit of time. And if we want to go backwards, if the map F is invertible, we can also talk about where X was in 1 minute of time ago, and so on. So depending on whether F is invertible or not, this collection of what we call iterates of X is called the orbit. And dynamics is the study of orbits. You want to know, maybe you want to know something about every orbit, a typical orbit, almost every orbit. The question is kind of over the long term, what happens? So that's dynamics in the sort of simplest form. And I'm just imposing differentiability because I like calculus. Okay, so so if I have a CR map, a dynamical system, then a symmetry is going to be an automorphism of the ambient space M called H. And when I say automorphism, I mean a diffeomorphism, so a map that is smooth with a smooth inverse. And we say it's a symmetry if it commutes with F. So applying H then F is the same as applying F then H. And another way of writing this is that F is, if you like, conjugate to itself via H. Okay. So just as symmetries of an object form a group, symmetries of a dynamical system form a group as well. So it's easy to see that if HF equals FH, then H inverse F equals F H inverse. And the composition of two symmetries is a symmetry. Okay, so I'll give a name to this group, S of F, for the symmetry group of F. And if F is CR, then this is contained in the group of CR diffeomorphisms. And in fact, it's a subgroup. Okay, so the diff R of M, the space of set of CR diffeomorphisms of a manifold M, I like to think of this as the universe of dynamical systems, invertible smooth dynamical systems on M. And what's nice about this is it carries a topology known as the CR topology. The topology gets finer as R increases. And the operations of composition and inversion are continuous. So this is a topological group. All right. So this is a subgroup of that topological group. And if F itself is a diffeomorphism, then the iterates of F are trivial symmetries, or they're symmetries of F as well. And we like to think of those as being trivial symmetries because you always have them. So if I look at F to the N, F is a diffeomorphism. So I can look at all iterates and I get the group, the subgroup generated by F. That is in fact a normal subgroup of S of F. Oop, that just went away. But so if we wanted to really examine non-trivial symmetries, you might take the quotient there by the normal subgroup and get a reduced symmetry group. So what about symmetries? Why is this a natural notion of a symmetry of a dynamical system? Because they map the natural objects of dynamical study to themselves, namely orbits. So just animating the relation that I wrote before and applying it to a single point, I can take F, X, I apply F of X, that's X in 1 unit of time. I could apply H, and that should be the same as first applying H and then applying F. Okay. So this picture, you could iterate this picture and stack these squares on top of each other, and you'll see this picture. So starting with a point X in M, I can apply F several times. So I apply F twice, then I get F squared, and so on. If I do this, I get the orbit of X under F. On the other hand, I could look at H of X and look at its orbit. And H being a symmetry says that the first orbit is literally taken onto the second orbit. Okay, so symmetries of dynamical systems preserve orbits. All right. Well, if you preserve orbits, you also preserve canonical quantities or sets, objects associated with these orbits. And so symmetries of a dynamical system preserve these invariants. So the simplest example are periodic orbits. So a periodic orbit is, skipped ahead, but a periodic orbit is a point P such that some iterate of F fixes P. Well, what if we look at what F to the K does to H of P? Well, you can see from the previous picture, or I'm just going to write down, this is H of F to the K of P, and this is H of P. And so therefore, if P is periodic for F, then H of P is going to be periodic for F as well, with the same period, or at least, well, with the same period, if F is, say, diffeomorphism. And not only that, but if you know what these concepts mean, and if you don't, that's fine. But multipliers, so eigenvalues of the derivative of F are also preserved by smooth symmetries. This is by the chain rule. And things like stable manifolds and so on are also preserved. So these are sort of canonical things that we associate with periodic orbits. So for example, if I had a point that's a sink, an equilibrium that's attracting nearby points, and I apply a symmetry, I get another sink. Now, if your map, for example, has only one such equilibrium, then you actually know that a symmetry has to preserve it. The next invariant is, the next object is invariant measures. If you know what those are, they're a very useful way to understand a dynamical system statistically, and symmetries preserve them. Finally, not finally, but the third example I'll give are the wandering and non-wandering sets of a dynamical system. Now, these can be defined in quite generality. You might be familiar with them in the context of, complex dynamics, where the wandering set is called the Fatou set, and the non-wandering set is called the Julia set. What's the wandering set? Well, you say a point is wandering if its orbit has a little neighborhood that never comes back. So it's sort of wandering off in all time, never returns. In some sense, this is the boring part of the dynamics because there's no recurrence. There's no way that you would ever compare the dynamics at one time at this point to the dynamics later on in the orbit, because it never comes back. So that's what a wandering point is. A non-wandering point makes up something called the non-wandering set. And a point is non-wandering if for every neighborhood of that point, there is some iterate that takes that neighborhood, maybe not the point itself, but takes the neighborhood back to itself. So it's the opposite of wandering. The wandering set is open, the non-wandering set is closed. And these are canonical objects that you can associate to a dynamical system. And in complex dynamics, these are called the Fatou and Julia sets. Now let's see some examples. So I don't do complex dynamics, but I brought in these examples because I think they're very nice for illustrative purposes. So here's a polynomial of degree 9, and it has a symmetry. Namely, if I take a primitive 8th root of unity, and I just consider multiplication, that's just a rotation by 2 pi over 8. 2 pi over 8. Then this is a symmetry, and I actually worked out the calculation here. So if I take f of h of z, that's f of zeta z, and if you plug it in, you get this. And you notice that since zeta to the 9th is zeta, you can pull it out, and this is zeta times f of z, which is h of f of z. And this, if you want to, symmetries form a group. If you look at the group generated by this is Z mod 8Z. This is actually the also the symmetry group for this polynomial, and the Julia set for this polynomial is this very pretty picture that has this eightfold symmetry. So there you go. We got it back again. Let's do one more example. So here's a degree 7 polynomial. Notice the coefficients of this polynomial are real. So there's one symmetry that comes from taking a primitive 6th root of unity. And for the same reason as before, this is a symmetry. It's easy to check. But since the coefficients are real, Z goes to Z bar, the complex conjugate, is also a symmetry, because I can bar like this, or I can bar like this, and I get the same thing because the coefficients are real. Okay, and together these generate a group. And what's the group? The snowflake group. And what's the Julia set? It's a snowflake. All right, so here's some fun examples just to show why symmetries of dynamical systems correspond to symmetries of canonical objects that you associate with these systems. So I want to explain to you, there's another kind of dynamical player. So I kind of lied when I said that that a smooth dynamical system is a smooth map, because that's what we might call a discrete time dynamical system, where time occurs in discrete iterates. There are also the so-called continuous time dynamical systems. That's where things evolve over time continuously. And what's a discrete continuous time dynamical system? It's a flow. So a smooth flow is just a map from R cross M to M, satisfying these two properties. So these properties, if you like, it's almost like these are conditions that you would want for time to act on a manifold. Another way of stating this is that if I can rewrite this, a smooth flow is actually a homomorphism from the real numbers into the group of diffeomorphisms. So I can think of it this way as well. So it's an action of the real numbers, a smooth action of the real numbers on the manifold. You might say, why diffeomorphism? You just said CR map. You didn't say something about these being diffeomorphisms. But the point is that if this map is smooth, then when I plug in minus t, that's another smooth map, and that gives me phi 0, which is the identity. So it automatically gives inverses. Okay. So I want to refer, when I have a smooth flow, I can also just think of it in discrete time, units of time. So the time one map of a flow is just the diffeomorphism you get by plugging in t equals 1. Okay, so I'm going to come back to the time one map of a flow, because there's some interesting questions you can ask about time one maps versus diffeomorphisms. So the first kind of simple question is, which diffeomorphisms are time one maps of flows, of smooth flows? Well, not all, because there's one kind of obvious obstruction, is that if you have a time one map of a flow, then as you let time go to 0, you approach the identity, which is to say on a topological level that this map has to be homotopic to the identity, or in fact smoothly isotopic. So suppose you assume that. My question is, which of these diffeomorphisms embed in the flow? All of them? Well, you can construct examples that show that not all of them do, but we'll come back to this question. Okay. And so just if you haven't seen smooth flows before, I don't want to overload you with information, but a smooth flow is always generated by a vector field. And the vector field is just given by differentiating the flow in the direction of time. So if I construct a vector field in this way, and so here's what a vector field maybe looks like in the plane, then the flow generated by this vector, maybe some places it's 0, the flow generated by this vector field, the orbits are going to be everywhere tangent to that vector field. And in fact, that vector field, if you like, represents the velocity of the flow. Okay. And so if you see a system of ordinary differential equations, first order, time independent, that's actually the same if you kind of combine things correctly. It's the same as, okay, it's the same as this equation. So any system of equations is really, it's of this form. And if you solve these differential equations, assuming the right boundedness conditions and the derivatives of uniformity conditions, then it will generate a flow. Okay, so vector fields and flows are kind of the same thing. Right. And so what's a symmetry of a flow? Well, I'm going to say that a flow is a symmetry of another flow if the two commute for every pair of time intervals, S and T. And so every flow is a symmetry of itself because the flow itself satisfies this kind of group property. Let me write it down. So if I take phi s composed of phi t, that's phi of s plus t, and that's phi of t plus s, and that's phi t composed of phi s. So any symmetry of a flow is a symmetry of its time one map. So in particular, if I have a time one map of a flow, then the entire flow itself sits inside of its symmetry group. So this gives a little bit of a deepening of an answer to the question I asked. The time one map of a flow has a lot of symmetry, right? Its symmetry group contains R as a subgroup. So you could sort of rephrase this question of not rephrase, but you could ask a slightly different question. What are the symmetries of diffeomorphisms in general? You know, can they always contain R? Well, if they contain R, then they embed in a flow. Okay, so what are the themes to this talk, or the theme that I want to convey is that symmetries are very special, right? Objects that have symmetries tend to be beautiful and pleasing. Well, dynamical systems that have symmetries are also beautiful, or they have other special properties. So I want to focus on three, keep track of the time. So I want to focus on three sort of instantiations of this theme. Noether's theorem, which says that symmetries can correspond to conserved quantities in physical systems. Then I want to turn to a question of Smale. I've written Smale's conjecture, but it's actually a problem or a question. And then something that I'm going to call symmetry rigidity, which is kind of this idea that if you have too much symmetry in a dynamical system, then you have a lot of symmetry. And this kind of rigidity holds in certain contexts. So I'll say a little bit about that. So starting with Noether's theorem, the symmetries of a physical system correspond to conserved quantities. So for example, in this top that I've showed you, if I start spinning a top like on the left in a certain position relative to a vertical direction, the direction of gravity, if I start spinning it there, it's going to follow exactly the same law of physics if I start spinning it over here, where I've just rotated around this axis. Okay. And what Noether's theorem says is that because you have this symmetry in the laws of physics, if you like, then there is a conserved quantity, which in this case is angular momentum. And having these conserved quantities can be very useful in solving Hamiltonian, what are called Hamiltonian systems, which I'll tell you about now. So what's Hamiltonian dynamics? It's a study of flows. It's a little bit more general than I'm going to tell you, but here's what Hamiltonian dynamics are in Euclidean space, R2n. So I start with R2n, and I take a smooth function, h, on R2n, real valued function. And this is called a Hamiltonian. Now, what's the interpretation of this function in terms of physics? Well, the first n coordinates of a point in Rn, I think of as the position of a point in Rn, and the last n represent the momentum. Let's suppose we fix the mass. And so those are the coordinates essentially of a velocity vector of a moving particle in Rn. So the qi represents spatial coordinates and the pi are momentum. I know it's weird to have space q before p, but that's how it is. So here's an example that we can actually interpret. I mean, we can write down all sorts of examples of h that I don't know what physical systems they correspond to, and you can still define Hamiltonian dynamics, but here's one that actually corresponds to a physical system. Namely, if I have a spring and a mass at the end of the spring, and this distance from the full squeeze point of the spring is denoted by Q, and you have a spring constant that's 1, and the mass of the object is 1, then this is the total energy of this configuration, taking into account position and momentum. So 1/2 Q squared, this corresponds to the potential energy, which is described by the spring constant, okay, and the mass is determined by that. So that's the potential energy. And this is 1/2 P squared is the kinetic energy. Why is that? Well, because momentum, remember, is mass times velocity. And in this case, our mass is 1. So that just equals V squared. So, and that's 1/2 of P squared. Okay. So this is the kinetic and the potential energy, the total energy. Okay, so what are Hamilton's equations? Well, let me just cut to a chase. There's some physics that goes on involving Lagrangian mechanics, principle of least action. And it says that if your system is following the physical laws determined by this potential and kinetic energy, then the trajectory, the change over time of the position coordinates and the momentum coordinates have to obey these two equations. So these two equations are a system of first order autonomous differential equations, ordinary differential equations. And so, as I said before, they generate a flow, and that's called a Hamiltonian flow. And remarkable property that just falls out of these equations is that this flow conserves the energy. So in other words, if I take a point and I follow its flow line and I compute h here, h is going to be constant along the flow line, which means that you can derive from the principle of least action, you can derive conservation of energy in these closed systems modeled by this Hamiltonian. Let me give you an example. So why not do the example I gave before? So if my Hamiltonian is this 1/2 Q squared plus P squared, describing a mass on a spring, then I can write down what the vector field is. So the first coordinate is dHdP and minus dHdQ. Okay, so this is a one-dimensional system. I sort of forgot to say. So here's what that vector field looks like. So if at the point PQ, I put the vector P minus Q, it looks like this. And this is the flow. You can just solve the differential equations. It's a linear first order differential equation. And so the flow is the flow where if you start at a certain position in momentum, you're going to move around the circle with the velocity that's proportional to your distance from the center. So it's just a rotation of the plane. And here's a picture from Wikipedia of exactly this. There's two things that might cause confusion in this picture. The first is that doesn't look like a circle, it looks like an ellipse. Well, okay, so probably the spring constant wasn't 1, or the ratio of the two wasn't 1. Okay, that's not a big deal. The other is, why is it going counterclockwise instead of clockwise? That's because if you look at the axes, velocity and position, or momentum and position, have been switched. And that's an orientation reversing map of the plane. So that's why. But here you can see exactly the real space is how Q is changing. And then the phase space, the QP space, is how the momentum is changing. So now I can tell you what Noether's theorem says. It says, suppose I have two Hamiltonian flows that commute. So in other words, one flow is a symmetry of the other. Then the Hamiltonian of the first is preserved by the second flow. So I probably should have gone back here and pointed out. Notice that these trajectories are tangent to these circles, and these circles are level sets of the Hamiltonian, right? Level sets are circles. Q squared plus P squared equals constant. And so energy is conserved here. And so a flow commutes with itself. So it preserves its own Hamiltonian. And what Noether's theorem says is that if there's another conserved quantity, then it actually produces a symmetry of the flow by producing the Hamiltonian flow and vice versa. So this is one sort of Hamiltonian formulation of Noether's theorem. There are other formulations where you have an action of a group, and then you have to define something called the moment. I'm losing the word for it, but you have to define an additional quantity that sort of associates to each element of your group some Hamiltonian, but it's a similar flavor. And so what do we take away from this? Well, we take away, this is exactly explains the top, because there's a symmetry in the dynamics of the top, and that corresponds to a conserved quantity, the angular momentum. So symmetries of a Hamiltonian flow, or at least Hamiltonian symmetries, are very special, and they correspond to conservation laws. And this is a very powerful idea in physics, and it extends well beyond this classical setting. Okay, so I hope I've given you some feeling for what Noether's theorem says, because it's, from a mathematical point of view, it's actually a very simple statement, and the proof is not crazy difficult either. Okay. So I'm going to move next to Smale's conjecture, which is actually a question, to be fair, but I'm going to call it a conjecture. So around the turn of the 21st century, Arnold asked a few mathematicians to give a list of their kind of Hilbert problems. So 20 problems that they thought would be very interesting problems to be solved in the next century. All kind of a little silly, but so Smale put together a list of 20 questions, and I think this particular question I like very much, and I'll try to explain to you why. So I'll state it as a conjecture, but it's really a question. The question is, does this conjecture hold? Okay, so what does it say? It says, consider the universe of dynamical systems, diff R of M, on a fixed manifold. So here the manifold should be compact. without boundary. So I said closed. Connected, because if I take two spheres, I could, like, there are symmetries I could do. But the typical diffeomorphism, well, maybe it doesn't even have to be connected, take it back, of a closed manifold has only trivial symmetries, meaning that the symmetry group of F has to be the group generated by F. Or if you like, the reduced symmetry group, the quotient is trivial. So what does typical mean? Well, he actually said precisely what he meant by typical. He meant dense. So the way he asked the question is, can every diffeomorphism be approximated by a diffeomorphism with trivial symmetry? Okay. And by approximated, well, if the diffeomorphism is CR, the question is, can you make it CR close? It means the first R derivatives don't change much at all. So that's one notion of typical. There's a stronger notion of typical that implies dense, which is what we call in dynamics generic. What does it mean for a property to be generic? Well, what it means is, if you look inside of this universe, which is a topological space, it's a complete metric space, and you can ask, is there a very large set on which this property holds? Very large meaning something stronger than dense, meaning large in the sense of bare category theory. So a large set in this case would be a countable intersection of open and dense sets. So an open and dense set is very large, but even if I take a countable intersection of open and dense sets, I'm going to get a dense set. And if I have a set like this, it's called a residual set. If I have two of these and I intersect them, they're still residual. So unlike dense, I can have two dense sets, like the rationals and the irrationals, you intersect them, they're empty. So if a property is generic, if I have two generic properties, then their union or their intersection, having both of the properties hold, is also generic. Okay, so I wanted to define this. There are very, very few properties of dynamical systems that are known to be generic. The only one I can think of is properties involving periodic points. This is a Kopell-Smale theorem that says that periodic orbits have to be hyperbolic and says something about stable and unstable manifolds. But think about it, it's kind of hard to imagine any property that could hold for, you know, such a large set of diffeomorphisms. And this puts a finger on something that you really would hope. You know, there are other properties you might think, and they're not generic. But so this is Smale's question or conjecture. Now, he formulated this question quite a while ago. And his student, Nancy Kopell, who's well known for her work in applied mathematics in biology, her thesis was, she was a student of Smale's, and her thesis was actually about this question. So what she proved is that on the circle, so if I restrict my dynamical system to be the circle, then not just is there a dense set of diffeomorphisms with trivial centralizer, but there's an open and dense. So it's a very, very strong sense of typical. So if I take any, the generic, well, if I take any CR diffeomorphism for R bigger than 2, I can approximate it in the CR sense by one that looks like this. It has some periodic orbits. Maybe these move around, but they're periodic. And the orbits are, these periodic orbits are, so these would be fixed points because they can't be periodic, but that are attracting or repelling. And then you would think if you had a centralizer, if this had non-trivial centralizer, you'd have to have some kind of flow in between that are connecting these periodic orbits. And what Kopell showed is that even if there is a flow that kind of fills in those gaps by a small perturbation, you can remove, there's no flow anymore, and that's a stable property. So it's a very strong result, but it only applies to the circle. It's actually false for r equals 1, which is very interesting. And it only applies to the circle. So this leaves open the question, what about higher dimensions? And this was answered, I think, about 10 years ago by Christian Bonatti and Sylvain Corvisier and myself. So we proved that on any closed manifold, the C1 generic diffeomorphism has only trivial symmetries. Okay. I might have used the word centralizer, symmetries. So just a couple comments about this. So going back to our question, remember I said, which diffeomorphisms embed in a flow, which diffeomorphisms are the time one map. This implies in a very strong way that if I take a C1 generic diffeomorphism, it has no symmetries other than itself. So it clearly can't be the time one map of a flow, because there you would have to have R. So this implies that. The latter result is quite a bit weaker. It was proved by Pallas in the 70s. But what's interesting is that even this weaker question is completely open for R equals 1. So no one knows the answer to this. And CR generic for R greater than 1 is open. There are a lot of really basic questions about diffeomorphisms that no one knows the answer to in the C2 topology, that we know the answer to in the C1 topology. So for example, does the generic diffeomorphism have a periodic point? Just does it have a periodic point? So in the C1 topology, the answer is yes. And that's Pugh's closing lemma. It's not really a lemma, it's a theorem. And no one knows C2. So could you find, for example, an open set of diffeomorphisms, or even just a little open set where generically no diffeomorphism has a periodic point? Anyway. So how do we prove this conjecture? I have time to say a couple words. So the first step, and there's a couple steps, but I can at least say something about what the first step is. So remember, I told you that symmetries map orbits to orbit. Now I want to show that generically a diffeomorphism has no symmetries. Well, if I can show that generically different orbits are different, any two orbits are different from each other in some sense that cannot be preserved by symmetries, then if I have a symmetry, it's going to have to map each orbit to itself. That's very close to saying that the symmetry is a power of F. It's not the same. But the first step is to show that any symmetry has to preserve orbits. And so this amounts to differentiating any two orbits from each other dynamically or using C1 data. And so we're able to do this by using the nature of the C1 topology. We make any two orbits, we make each orbit sort of contain regions where the derivative gets bigger and bigger and bigger. And we can do this in a way that each orbit looks different from any other orbit. And so you can't match two orbits together by symmetry in that way. And that uses the C1 topology where we're allowed to make little local perturbations. In the C2 topology, if you want to perturb a diffeomorphism, you can't do it locally. You can't sort of fix a picture that you want to plug in and have that occur. Okay, so it's kind of some sense of how this result goes. But it uses a lot of what is known about C1 generic diffeomorphisms. All right. So finally, and I only have a few minutes to say something about this, this is actually the subject that's really interesting to me right now, is that of symmetry rigidity. So what should this say? Well, it should probably only hold in certain contexts. And what it should say is that a little bit of extra symmetry implies a lot of symmetry. There are results like this in kind of when we talk about symmetries of objects or symmetries of metric spaces and things like this, but not so much in symmetry of dynamical systems. Here's something that kind of has this flavor. So this is a fact. If I have a polynomial and its Julia set has a symmetry of infinite order, meaning just that that symmetry does not have a power that equals the identity. So infinite order just meaning that h to the k does not equal the identity for every k. Then the Julia set is either a circle, an interval, or the whole plane. And once you know that the Julia set is one of these simple examples, you can actually say what the dynamics are as well. So this is a kind of an interplay between dynamical symmetry and symmetry of objects. This is not clearly not true of general kind of compact sets, but this is true of Julia sets, which are generated by dynamical systems. And essentially the symmetries of the dynamical system of the Julia set give symmetries of a dynamical system, and then you're able to conclude. Now, what do I mean by symmetry? This is definitely true if you just look at Mobius transformations as your symmetries. It's probably true if you look at diffeomorphisms, as I'm told, but I don't know the exact proof. And I'll just end with a few words about a project that I'm working on with Daniela Damjanović and Disheng Xu. And this concerns diffeomorphisms, and it's related to the question of which diffeomorphisms embed in flows. So inside of the space of C infinity, right now it's very much focused on examples. We have some interesting examples where this holds. We want to locate some highly, and this is not all highly symmetric systems, and this is not all manifolds, but we want to locate dynamical systems that have a lot of symmetry. So for example, time one maps of flows have a lot of symmetry, but we need that these systems are pretty chaotic, and we need that they have some internal symmetries as well. So for example, in a paper we wrote recently, we considered the time one map of geodesic flows in negatively curved manifolds. So these have some internal symmetries, and we look at perturbations of these flows, and we look at time one maps, but they have sort of a mix of chaotic and highly symmetric properties. And then we show that the systems we're interested in have this wonderful property that if you perturb outside of the highly symmetric systems, so you take a perturbation, okay, then either you didn't actually move out of the highly symmetric systems, so you've just perturbed like this, or no matter where you move when you perturb out of the highly symmetric systems, you suddenly have trivial symmetries, or not actually trivial, but up to finite order groups, trivial symmetries. So these are systems that we call, this is a phenomenon we call symmetry rigidity. And we've shown this for flows, for time one maps of certain flows. And we've also shown this for systems that have like symmetries of larger Lie groups. We take a diffeomorphism, but it has a large symmetry group. And then we can show that these systems, when you perturb them, have no symmetries unless they were actually belonged to the original class. So this is kind of where I'm at now, one of the projects that Daniela and Disheng and I are very interested in. And I wanted to give you some sense of the history of how we got there. So thank you very much. And I'll end on this picture by Kurt McMullen of the Fatou set of a rational map on the sphere that has A5 symmetry, which is pretty cool. Thanks.
Okay, thanks so much, Amie. I've turned my sound and my video on because I am going to send some questions to Amie from the audience, and I even have one too actually, but I'm going to do mine last. So let me start with a question from Dylan Thurston. He asks, would an attracting periodic point be in the non-wandering set? It's not in the Julia set, so there's some slight difference.
Any periodic point is in the non-wandering set. Any periodic point is non-wandering because every neighborhood of that point is going to come back and hit itself when the point comes back. So, yeah.
Cool. Okay. By the way, you're getting lots of praise in the chat. I hope it's saved, so you'll be able to see this after, Amy, because I'm keeping you busy answering questions. But
all right. Yeah.
And Jitsi Huang asks, in the particular equations you wrote down, like they point to z to the 7th plus 1.5z. Was there a reason for that particular coefficient, 1.5? Does it just make the prettiest picture, or like does it need to be that exact coefficient for the thing you said to be true?
No, yeah, no. I randomly, I sort of played around until I found coefficients that made a pretty snowflake. But there's nothing, you can move those coefficients a little and you still get the pretty snowflake, or a pretty snowflake.
Cool. Okay, I'm going to ask my question. Oh, somebody says of your talk, Skona Britton says it reminds her of why she likes physics. That's high praise. Okay, so my question is, and maybe I couldn't tell if the last theorem you stated sort of partially answers this, but if you have, I don't even know if this makes sense, but if you have a diffeomorphism which you know has boundaries, like let's say the time one map of a flow, so you know there's an R there, would you expect a la Smale that sort of, so to speak, a typical thing that has an R's worth of symmetries has only an R's worth of symmetries and no more? Is that even a well-formed?
Yeah, so I mean, I can answer that. As I said, I mean, this very last project is to sort of say, either if you're anywhere near these particular flows, either you have an R's worth of symmetries or plus a finite group, or you have no symmetries up to a finite group. But yeah, that's, I think, so, oh yes, and I should mention, oh, but goodness gracious, I forgot to write down the name. So Damjanović, oh, and I've got him in the wrong order, Martin Legui and Damjanović, and I think I've forgotten the third person, have studied centralizers of flows. So there's some similar facts known for C1 generic flows, but the question you asked is a very good one.
Okay, well, we are at the end of our time, and I think we're done with the questions. I hate to end on you telling me I asked a good question, but I guess but thank you so much, Amie. We so much appreciate. As I said, the chat is full of praise. I hope you will click over and look at everybody commenting on what a great talk it was. And thank you so much for accepting our invitation.
Thank you. And I have one more thing to say, which is behind me, virtually behind me, is a photograph of a blackboard that I drew last year in Paris. And the photographer, Jessica Wynn, has a beautiful collection of photographs that's going to be a book that she's publishing next year of mathematicians' blackboards. And she today at 2 p.m. Mountain Time is going to do a presentation through the Princeton Press. So I want to encourage everyone to attend and see some of her pictures, and her presentation's pretty awesome.
Those pictures are pretty great. I agree. Okay, awesome. Thank you, everybody.
All right. Thank you very much.